A warm welcome to this presentation by Team AI Visionaries on the paper titled Deja Vu Continual Model Generalization for Unseen Domains. Deep neural networks often face the problem that they underperform when they face data that is different from the data that it has been trained from. That is, it is from a different domain. It underperforms during this period where it tries to adjust to the new data from the new domain called the unfamiliar period. This paper tries to come up with a framework called RATP that tries to address the problem. A good example to understand the problem would be surveillance cameras, which become blind on rainy and snowy days when they have been trained on images from sunny days, and lung imaging analysis were not working on other forms of COVID. Existing solutions, domain adaptation and domain generalization. Domain adaptation is basically retraining the neural network, which is slow, and domain generalization is coming up with generalized neural networks which forget from what they have learned from the previous domains. To tackle these weaknesses, the RATP tries to achieve three objectives: TTG, which is target domain generalization, so that the model performs well or when it faces data from new domains during adaptation. TDA, target domain adaptation, so that it performs well on the data after it has adapted to the new domains, and forgetting alleviation, so that it retains information that it has learned from the previous domains. The RATP framework thus comes up with three modules to achieve the objectives. The first is a randmix module, which achieves target domain generalization by coming up with artificial data from the source domain data. It tries to come up with artificial data by by an algorithm called randmix. The next is the pseudo labeling mechanism. When we come across data from a new domain, it does not have its labels, so we need to come up with its labels from through a pseudo labeling mechanism, and this is achieved by T2PL, and this enhances TDA. Finally, there is PCA, which basically tunes the neural network and uh, gives us and achieves TDG, TDA, and forgetting alleviation. Let's look at the descriptions of all of the modules. This is our problem statement. We first have our source domain data. The S superscript indicates that the data is from the source domain, and we have both the inputs and the outputs. Then we face data from T unknown domains, and they only have their inputs. We do not have their labels, and we need to adjust our neural networks to tackle all of these labels, all of these new data. Since it is a deep neural network, we are expressing it as a feature extractor f theta at the bottom and the classifier g omega at the top. The randmix module basically achieves generalization by creating synthetic data from the source domain. It uses n auto encoders. Each auto encoder takes the data and transforms it into a new set of data and adds in random noise using the ADA-in algorithm. It takes all of the n autoencoders, uh, gives us a new gives us a new data, and we weight each of the autoencoders results and average it by their weights and pass it to the sigmoid function to squish it. Then we pass this data through the neural network, and if it is able to be classified using high enough confidence, R-con is the hyperparameter for confidence, then we have a new artificial data point x bar x tilde. The pseudo labeling mechanism creates labels for our unseen data from the new domains that we see. It basically tries to define centroid points for each of the domains that we have found. First, it takes the outputs that have been classified with the most confidence, that is our top 50% the data points which have been classified with at least 50% confidence. It takes all of those data points and it creates centroids for each of the classes that we have seen. Then it further refines the data points by taking only those data points that are at least 50% close, that are in the top 50% in closeness to the centroids. Determining the closeness from the centroids is done using basically the dot product, that is the cosine similarity. Finally, after we have got our refined set of data points that are representative of each domain. We then use our k-nearest neighbor algorithm to assign the pseudo label to each incoming data point. Finally, prototype contrastive alignment, or PCA. It assigns the neuron weights as the prototypes for each class, and it comes up with three loss functions. The first loss function penalizes um, data points that are further away from the data points, and it ensures that the data points come close to their prototype. Then the contrastive alignment penalizes cross similarities between two classes, and it ensures that the data points of one class are different from the other class. And the knowledge distillation ensures that we do not forget what we learned from the previous domain. Once we get all of these three loss functions, we try to optimize it by changing f theta and g omega, that is by tuning our neural network. This is the RATP pipeline, which shows all of the three algorithms, T2P, RANDMix, and PCA, being applied to new data that we come across. As we can see, when digit recognition is done across 5 datasets, all of these 5 datasets, although they tackle the same problem of recognizing digits from 0 to 9, they are significantly different from each other, and then can thus be considered to be data from 5 different domains. And in this case, and we can see that in almost every um, in almost every case, the RATP framework outperformed all of the other frameworks available. Similarly, it outperforms other frameworks on the digit PACS case. This is the citation of the paper and the link for the code. Thank you for your patience.